Okay.
Okay, so you have a paper in front of you dealing with the average value and the average rate of change. Okay, these two concepts, if you use the same exact function and you work out the average value of that function, the average rate of change of that function on an interval, you get two completely different answers. So it's not a 50-50 guess as to which one you're going to use. You need to decide which one you're going to use by the context of the problem and how everything is worded. Okay? After you drill this enough times, it becomes a very, very simple task. But until you drill it, it's like, you know, 6 of one, half a dozen of the other. You don't know which one to do. So let's practice a little bit on it, okay? This says average rate of change of a function on AB is equal to the function evaluated at B minus the function evaluated at A all over B minus A. What does that look like to you? Definitely slope, right? Okay. So this is the slope of the secant line connecting the endpoints on the interval of the function. I would like for everybody in that space provided for you right here, I would like for you to draw this picture. So I'm going to create a XY axis. And I'm just going to create some kind of a quadratic. Let me see. I'm going to just go like this. Okay. And we're going to create this picture twice. Once up on top and once down on the bottom, so we can see the difference between. And I'm going to pick an A value over here that's negative, but not too much negative. So there's my point. And I'll pick a B value over here, and I will go up to wherever this B is. And pick a point. So this could be my function f of x, which means this is B f of B, and this is So using that interval from A to B and that particular function, could you draw something that would represent the average rate of change of f of x on AB? Everybody draw it? You know what you're supposed to draw? You're supposed to draw the secant line. So go right through, cut right through both these points. Draw a line going right through them. Okay, if you miss a line, just go back and make your points a little bit bigger. And I never like to cut through my labels, so I'm going to rewrite my label. So the average rate of change of f of x on AB is equal to the slope of the secant line. Is that okay if I write M for slope and SL secant line? Now, I know that what I'm about to show you, you can't literally do. It's impossible to literally do this, but I'm just going to talk a little bit about the slope of any tangent line as we go through this function from A to B. If I'm at A, then my tangent line looks like this, and the slope is definitely negative, and it's, you know, further, it's steeper than -1, right? Okay? And then as I continue, my slope is getting bigger, right? It's still negative, but the slope is increasing because it's getting closer to 0. So negative numbers, as they approach 0, they're increasing. So the slopes are increasing. Obviously, the slopes are increasing. The function is concave up, right? And that's a definition of concave up, f prime increasing. So as I take a look at all these slopes, I got negative slopes, still negative, still negative. I got a 0 here, don't I, with my relative min? And then my slopes turn positive, 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 positive. So wouldn't you kind of guess that you have a lot more positive slopes than negative slopes? Yeah, no?
Yeah.
I would think so. So if I could take every single slope of the tangent line all the way around my curve, and I could average them all up by adding them all up and dividing how many I have by how many I have, I would have my average slope, or my average rate of change. Okay? The thing is, I can't add them all up and divide by however many I have. It's impossible. There's an infinite number of them. So theoretically, only I can do this. I can only do it theoretically. I can't do it physically. However, the slope of this secant line that connects these two is the average slope of all these slopes going all the way around. And the mean value theorem for derivatives tells you that somewhere down here, there's a c value on my x-axis, where the slope of that tangent line at x equals c is going to be the exact same slope as my average value, average rate of change. Does that make sense? Okay, so I'll stay away from that mean value theorem for a second, but this is what I need you to understand, that the average rate of change is the average slope. It's what you would get if you could add up all the slopes and divide by however many you have, which you can. Got it? Okay. You can get that answer simply by taking the slope of the secant line that connects your endpoints. Good enough. Here you have this. And this is the slope of the secant line would be f of b minus f of a all over b minus a. I'm not going to put that in parentheses. All over b minus a. Literally, change in y's over the change in x's. Pretty simple. All right. The next thing in your problem here says the average value of a function. The average value of a function. The average value does not mean the average rate of change. The value of a function is considered its y-coordinate. So if I said to you, what's the value of f of x at a, you should tell me f of a. What's the value of f of x at 2? You might tell me 1, if that's the point 2, 1, I don't know. But if I ask for a value, find the value of f of x at x equals whatever, I'm talking about the output, or the y value. So when you find an average value, you're finding an average y-coordinate. Got that? Please, on your paper, where it's nice and bold, where it says rate of change, average rate of change, circle the words rate of change and write slope. Or put the letter M, something like that. Down here on the second one where it says average value, circle the word value, bless you. Circle the word value and put what? Put the letter Y. Okay? Because it's a Y value, it's a Y coordinate. It's a height. So now I want to describe with you about the average value. We did this on a video before. It was question number 8 from your accumulation worksheet, and I explained average value to you, and you took notes on that. So you've done this once already. I just want to re-emphasize it and show you the difference between the two kinds of questions, okay? The average value of a function, I'm going to take the same picture as best I can, and I'm going to try and replicate it here, on a point here, right? A point over here and up here, and it looks like I'm coming down here. So I'm going to try and replicate this picture as best I can. I don't know how good that is, but it's going to have to work, okay? So here's my A, f of A. Here's my B, f of B. Here's my B. Here's my A. Okay. I actually made this picture twice. I'm going to do it one more time. You guys do it twice. On the paper. And we're just going to let that go. Okay. Does it look okay? You guys are doing your own, and let me just back up and take a look at my own. Yeah, close enough, eh? Not perfect, but never mind. Okay. So, the average value can be thought of in terms of comparing the area under the curve on one graph, bounded by the curve itself, which is my f of x, and the x-axis, and whatever boundaries you set, for in this case, it's gonna be x equals a and x equals b. So the area bounded by that would be in this region right here. And I like shading my area up and down, just like the calculator does, it goes brrr, right? Because we are talking about an infinite sum of what? Little rectangles, okay? So this area right here, which is known as the integral from a to b of f of x dx, is equal to, you know what, right before you write that, you guys, put down here, area under curve. Area under the curve is equal to area of a rectangle. Now what rectangle, you might be saying? I'll let you get caught up. You with me? So just look up here for a minute, and as soon as you get done your drawing, there's still a couple people still drawing, okay, but I just want your attention as we go through the next piece. And I'll give you a minute to write anything you want at that point. If I were to consider my length between A and B, so this is the length I'm dealing with between A and B. Okay. And I wanted to know how high I could create a rectangle that would be the same area as the area under the curve over there. So if I had a height that hit that vertex or hit that relative min right here, and I talked about this area right here, does the area of this rectangle match the area bounded by the curve? No, it doesn't. I'd have to go a little bit higher. Should I go all the way up here? If I went all the way up here and shaded all that in and made a rectangle with this base from A to B and that height, wouldn't that be a whole lot more than what I need? So if this is not enough and this is too much, then somewhere in the middle must be just right. So let's see, do you think here? Do you think maybe at this point right here?
Yeah.
Let me draw it, okay? I might end up erasing this, but let's just take from point A and let's go across and let's shade all of this in.
No.
Okay? Do you think that this area matches that area?
No.
You say no? Do you think it's too big or too small?
Too big.
How do you know?
Because it's including what's on the left and that stuff. And the you know what I'm trying to say, right?
I do.
And
I'm having fun watching, listening to you do it. But go ahead. It's including
it's
what's
including
on the
what's
left.
on the left and on top of that. And the half circle, or whatever that is.
Yeah, it looks like half a circle, but you can't really say it's a half circle, but I get you. Okay? So I'm not supposed to have this half circle, right? I'm not supposed to have this curve and whatever's above it. That's not here. But I am missing this little, I don't know, I call it a triangle shaped thing, even though it's not a triangle, right? Because one side of it's actually curved. But there is this little piece that I'm missing. But I have all of this much extra and all of this much I didn't count. That doesn't counteract. Okay, it counteracts way too much, doesn't it? Okay, so I think that the height that I just made that was a little bit too high. So I'm going to erase that, and then I'm going to put my picture back into play, okay? If I can. So this is not enough. This is too much. What if I went right about here? What do you think there? Right about that area? Think that would work?
Maybe.
Wouldn't I be counting this down here in this little curved part section, this little moon looking piece? And would that area that I'm counting be enough to counteract the fact that I'm not counting this little triangular piece and this bigger triangular piece? Do you think that would counteract it?
Yeah.
Not quite.
Not quite? You think I gotta go a little higher?
Yeah, just a little bit.
Just a little bit higher, like that?
That looks better.
Yeah.
Okay. So I'm not exactly sure where it is. It doesn't have to be perfect either. But wherever it is, there has to be some height. Doesn't there have to be some height? If my lower one was too small, my higher one was too big, then somewhere in the middle had to be just right. So wherever that height is in the middle, that height is called the average value of f of x on AB. Whoops. That's the average value. It's the average height. It's the average height. So the area of this rectangle is base times height, right? Base times height. What would my base be if I'm going from A to B? What if I went from like -2 to 7? How long would that be? 9. So mathematically, how could I represent that with A and B? What if this was like -2 and this was 7? You said that would be 9. How do I represent that as a formula? B minus A. Okay? 7 minus -2 turns it into 7 plus 2 makes 9?
Yeah.
Okay. So this is B minus A is my base, and the height is my average value. And that's still equal to the integral from A to B of f of x dx. Now, I'm trying to create a formula for the average value. So I want to solve for this AB, which is average value. In order to solve for AB, I need to divide by whatever is being multiplied by. So I'm going to divide this by B minus A, and I'm going to divide this by B minus A. I'm going to write average value equals, which means I'm taking the right side of my equation and putting it on the left side of the equal sign. Therefore, I'm going to take what's on the left side of the equation and put it on the right side of the equal sign. Except I'm going to change the way this looks. I'm going to change this so that it looks like 1 over B minus A times the integral from A to B of f of x dx. And that becomes a formula for the average value of f of x on the interval between A and B. Now I want you to get theoretically what it means as well. We talked about over here the average rate of change would be adding up all of the rates of change or all of the slopes of the tangent lines and dividing by how many we have, which we can't do. It's impossible. There's an infinite number of tangent lines to this curve between A and B, so therefore there's an infinite number of slopes to the tangent line. Over here, I want to find the average value of a function, which means the average height of a function. So how many y values exist between this point and that point? How many y values exist on this function between A and B? An infinite. Did you say finite? There's an infinite number of points between any 2 points, aren't there? You can always go in the middle, you always go in the middle, you always go in the middle. There's an infinite number of points between A and B, so therefore there's an infinite number of y values between A and B. But if I could, which I can't, but if theoretically I could, add up all the y values between this endpoint and this endpoint on this graph. I add up all the y values and divide by however many I have, which I can't really do it. It would give me my average y value, wouldn't it? And the average y value is this. So I can't physically do this, but it's mathematically equivalent to this, which I can physically do. The average y value would be right around here. And look at it, just think about it. These y values are higher, these y values are lower, 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 higher, 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 higher. The average y value has got to be somewhere between the lowest point and the highest point. Okay, it's not always smack dab in the center, it possibly could be, right? But it doesn't have to be, it's just somewhere in there. Okay. So you need to know both of these formulas, and you need to be careful with this. This average value of f of x has to be the function that goes in that integral, in the integram. And this right here, this average rate of change of f of x, this f of x has got to be the function you evaluate on your numerator. Alright. So I'm hoping that makes a little better sense. Can you draw those pictures? Do you have those pictures on your paper?
Yeah.
Okay. You wrote it out a little bit? Average rate of change means average slope. Average value means average height. Alright. So on the very bottom of this page, it says something here. Anybody want to read that to me? I'm going to erase the board. Courtney, read it out loud, please.
The last part.
Yep.
The average rate of change of an object's or particle's position function is mathematically equivalent to the average value of its velocity function.
That just sounds like a bunch of words, doesn't it?
Yes.
Anybody make sense out of it? Okay, I have to write it down on the board so I can like circle things and tell you what's going on here. And we can really get at it, okay? The average rate of change of an object's position, no, did I write position?
It says or particle's position.
Objects or particles position function is mathematically, you know what? Give me a sec. Is mathematically equivalent to, so equals, the average value